These are your video notes for environmental issues, ecology, and human impact. So we're going to start talking about renewable and non-renewable resources. Non-renewable resources are resources that cannot be replenished quickly by natural processes. So this will include coal, it includes oil, it includes natural gas, and it includes nuclear. And they're not always bad. Of these, yes, we do want to avoid using coal and oil to the maximum possibility. Natural gas is kind of the next one to avoid. And then nuclear is actually by far and away the best. And really for any modern transition to renewable resources is actually critical to make the transition from non-renewables to renewables. For renewables, though, that's going to be things like wind, solar, hydropower, geothermal, forestry, right, trees. These are all resources that can be quickly regenerated and used by us repeatedly in our own lifetimes, and they don't run out. So ultimately, the goal of energy usage is what's called sustainable development. So basically, being able to go about our daily lives, doing the things that we want to do, using the technologies we want to use, but doing so in a manner that does not permanently deplete natural resources, and also allows future generations to use the same resources and experience the same experiences that we have. And this is a major driving concept in environmental science and is actually one of the overarching concepts for the course if you ever do take a higher level AP course in environment or environmental systems. So we're going to do a quick tour, not too detailed, of a variety of environmental issues, and we'll start with ozone depletion. So ozone is a protective layer of gas, O3. There's 3 oxygens that help absorb ultraviolet electromagnetic radiation or sunlight, right? This is the kind of sunlight that can, or wavelengths of light that cause cancer, for instance, or can mutate or have higher rates of mutations for crops when they're exposed to extensive sunlight and cause cataracts and a whole bunch of other health and environmental issues. So preserving this layer is an important aspect of maintaining environments. And one of the things that we have actually done in the past 50 or so years is produce what are called chlorofluorocarbons, or CFCs for short, that initially were used as refrigerants. They were used in things like air conditioners and in aerosol cans as propellants, but they ended up actually reacting with and permanently destroying ozone, and that's part of the reason why we still have the ozone layer hole that we have, because chlorofluorocarbons can stay in the atmosphere for hundreds and hundreds of years. So we have actually stopped using chlorofluorocarbons. The ozone hole that we see every year over Antarctica has not significantly worsened, but it's not really getting any better. And part of the reason is because these CFCs linger for hundreds and hundreds of years. So here's just a quick image. Actually, last year, 2020, we had documented a record-breaking ozone thinning. It's not really a hole, it's just a thinning of the ozone layer above Antarctica. And the Dobson units are what's used to measure the thickness of it, but basically the colors are on the right with the key, and the average ozone thickness is somewhere around 250 to 300. That's pretty typical, especially kind of in the middle of the Earth equator and kind of north and south of it. Usually as you go up to your northern latitudes, you get more ozone, but every October, September, November, the late winter for that part of the year, you get, because of the way the Earth is tilting and the cooler temperatures, and the way sunlight reacts with ozone actually contributes to it naturally breaking down. But again, the CFCs exacerbate this and make this worse. But you can see there's the ozone thinning, the ozone hole. It's over Antarctica, and this is October 2020. So I'm actually going to show you a quick video. We can watch this together. Let's see if I can. Let's see if I can click this. So what you're looking at is a time lapse from NASA of the thickness of the ozone layer. The green is a thick layer. The light blue is kind of an intermediate, so is the yellow, and the darker blue you get, the purpler you get, the thinner the layer. And what you're going to notice is as you move through your October and November months, the thickness of the ozone layer is markedly thinner, but it improves and actually completely resolves by about December. And this is a typical annual cycle of ozone. We can talk more about why this works the way it does later if you guys want, but I'm actually going to play this one more time and let you look. There it is, very, very well defined. And then it repairs. All right. Second environmental issue, acid rain. So acid rain is solely due to the burning of fossil fuels from our emissions in factories and industries. So when you burn coal, natural gas, oil, you are releasing two major gases into the atmosphere. These are nitrous oxides and sulfur dioxide. Pens. Nitrogen oxides, sulfur dioxide into the atmosphere, and these react with water to form mild nitric acid if it's a nitrogen oxide, and a sulfuric acid if it's a sulfur dioxide. So in the diagram, you have the emissions from factories. You've got these two gases mixing with water in the atmosphere, forming weak solutions of nitric and sulfuric acid. When that is part of the water cycle and condenses, it then falls back to Earth as a form of acid rain. And the effects of acid rain are a variety on plant life. This is what's called the Black Triangle region of Germany, Poland, and the Czech Republic, Czechia. It's called the Jezera Mountains in Europe. This is 2006. You can see the effect of a forest after a period of acid rain. This is the effect of acid rain on a sandstone statue, but limestone does the same thing. It's a very porous, soft rock that is basically eaten away by the acid rain in a chemical reaction. So there's damage to wildlife, there's damage to cultural sites and architecture. But fortunately, over the past couple decades, we've been able to go from pretty acidic rain. This is acidic rain, pH of about 4 in really the eastern portion of the US in the 80s, has pretty much been completely rectified. We're in the upper 4s, the lower 5s on average here as of 2016. And again, the average pH of rainfall today is about 5.5. Rain is naturally slightly acidic because of the carbon dioxide in the atmosphere. And when water and carbon dioxide mix, you have a mild carbonic acid. So it is natural and normal for rain to be slightly acidic. It shouldn't be this acidic. This change, which is a good development, is an example of the Clean Air Act. and the benefits of regulating businesses and emissions on the health of our water quality. And if you want, you can go ahead and watch this GIF or GIF, I'll let you decide, and use your phone and it'll actually do a time lapse between these two dates. All right, environmental issues number 3, climate change and global warming. We have an atmosphere that traps gases and retains heat. That is a good phenomenon. It's a natural phenomenon, but the problem is that we are speeding this phenomenon up and we are exacerbating it beyond its normal boundaries. And we're doing that because we're releasing ridiculous amounts of carbon dioxide in quantity and methane in its potency. Methane is actually the most potent greenhouse gas that we continually emit in large numbers because it traps heat actually even better than carbon dioxide. We release the carbon dioxide because we're burning fossil fuels. I mean, that's it. It's the burning of coal, it's the burning of oil, and a little bit of the burning of natural gas. You release that into the atmosphere, and it traps the heat radiating down from the sun and does not permit it to escape into space. And the end result, it's a mathematical certainty, there's no way to avoid it, is an increase in temperature. So over the last 50 years, this is the baseline that we're comparing this to about the 60s, basically. What have we seen in the past decade? Well, we've seen, and this is in Celsius, increases of 2 to 4 degrees Celsius at our poles, especially the North Pole, the Arctic Circle, and basically everywhere on the planet's been heating up. Anywhere from a couple fractions of a degree Celsius all the way up to a consistent 1 or 2 degrees Celsius. Right? This is what we're talking about when we're saying we're experiencing global warming. This is not a natural process. And it's not a natural process that would ever happen this quickly, right? You have periods of heating and cooling on Earth, but they don't happen that incredibly fast. This is the same kind of thing. It's just predicted out to 2060. And again, it's showing you the exact same thing. Your poles do tend to be more affected. Those are the areas that have the greatest temperature swing potential. But this is the future of our planet, and a lot of the discussion about global warming needs to start turning to how do we cope and deal with it. So some evidence of global warming and climate change. I'm just going to show you a quick kind of overview and tour of some lines of evidence. Ice sheet evidence and the recession of ice sheets. Africa is one of the last kind of equatorial regions on Earth that actually does still have ice sheets, but it's rapidly losing them. You might have to zoom in a little bit if you can figure out how, or you can probably actually even Google this image. But as far back as just 100 years ago, we had a complete ice ring all around the top of Mount Kilimanjaro, and now it's basically completely gone. This is 2011. I didn't have a more recent image, but there are basically no more glaciers in Africa. There are glaciers receding all over the world. I was just in Iceland a couple of years ago, and I had the opportunity to walk on a glacier, and just the sheer amount of recession and disappearing ice it's a very emotional experience when you're actually there looking at it and you're seeing these sheets of ice just slowly die and kind of retract and pull back up and disappear. So there's the ice sheet lines of evidence. Greenland is also another one because ice that's on land, when that melts, contributes to sea level rise. Also, increasing temperatures actually cause water to expand. It's just a property of water. And actually, most of our sea level rise is due to expanding water rather than adding water from ice. But nevertheless, you will get sea level rises. A lot of people will say, hey, this is all completely natural. And it's a twisting of the truth. I mean, yeah, changes in temperature are natural, but not like this. So basically from the late 1800s to now, this is a graph showing you what you would have supposed to observed given natural drivers only. What would the temperature on this planet have been like basically if there were no humans? And it would have essentially been unchanged for the past 200, 150 years. Adding in human activity, and actually human activity only, if you just look at human activity and the burning of fossil fuels, you get the red line. From the I would even say back here, to the mid-1900s and onward, the observed temperature, which is the black line, corresponds almost directly and is predicted by the human drivers only data. Humans are driving global warming. There's no ifs, ands, or buts about it. The data is conclusive by now. We are causing this planet to heat up. Another interesting graph that I think it kind of drives the point home is the temperature change over the course of a year. So you can see the months on the x-axis. You can see the deviation from normal kind of on the y-axis, but the point is the higher up you are, the hotter it is. And as you go from your 1800s to current day, and here's 2021, you can clearly see a shift. And actually, if you go over to your axis, you're at about -3 to about 1. There's a 2-degree shift, 2 degrees Celsius over the past 150 years. An increase in temperature, right? And here's March 2021. This is our current path right here in purple. So we'll keep an eye on that and see. But basically, every summer that we've had has been a record-breaking summer, and that trend is very likely to continue. Here is atmospheric CO2 data from an observatory in Hawaii, and the red line is the actual CO2 concentration in the atmosphere. Here's kind of the infamous 400 parts per million that we've blown past in the past 10 years. We're well above that. We're approaching now 420 parts per million. And the trend line is in black on top of it. But what I want you to realize, at least from this, is the jigsaw pattern, or notice the jigsaw pattern. Why is there, and it's not related to global warming per se, but why is there this sawtooth pattern? Why? It's very predictable. It's actually incredibly consistent. So what's going on there? And we'll talk about that during class. I'm not going to tell you here. I want you to think about it, but we can discuss that too. This is basically the same data. You have the line for your CO2 levels in the atmosphere, but it's overlaid with the temperature. This is the effect of, it's showing you that there's a direct causal link between the amount of CO2 in the atmosphere and the temperature. One is causing the other. They're not happily and coincidentally related. It is a direct causation. CO2 increases cause greenhouse gas, or cause heat to be trapped, and the average temperature increases. And this is extremely apparent if you're honest about the data and you're willing to come to the scientific conclusion without the bias that comes with a whole bunch of other stuff. So here's your temperature from the 1980s onward, consistently above average every single year. And really this all starts with the Industrial Revolution. Right? Once we start burning fossil fuels, having factory emissions, that's kind of the time period where this all starts to go. All right, environmental issues, loss of biodiversity. So loss of biodiversity is typically due to things like deforestation, fragmentation, which I forgot to add on here. Fragmentation is when you take a forested environment or a contiguous land environment and you cut it up using roads and highways and developments, and you basically fragment the land. into little pieces. Pollution, climate change, we'll talk about biomagnification later, invasive species, all of these contribute to an overall loss of biodiversity. And the consequences is that it affects food. For us, at least, for our personal self-interest, it affects loss of food, industrial products, the number of medicines we can produce, because a lot of those are actually derived from plants. And this is not even addressing the impacts on food webs and food chains and the interaction between organisms, right? Eutrophication, we've talked plenty about, so I'm not going to spend too much time on it. You guys know that eutrophication is the fancy word for an algae bloom or an algal bloom. And we've talked in length about how that happens, so I'm not going to review that here. But I will kind of give you some images. This, I believe, is a picture of Lake Erie when I looked it up and put it on here earlier today. I just didn't put the caption with it. But you can see the algal bloom from space in Lake Erie, and a before and after picture over here. And you can also probably Google some more pictures. Again, the result of this is that you have no oxygen in the water and you have mass suffocation. Deforestation, it's self-explanatory. You're cutting down forests due to lumber demand, development, etc. So again, the consequence is a decrease in biodiversity. There's obviously going to be a decrease in photosynthesis and primary productivity, the decrease in producers, because they're not there to fix and capture CO2 from the atmosphere. You're going to have local increases in CO2 that then spread to surrounding areas in the atmosphere. You actually disrupt the water cycle because plants stop transpiring water into the atmosphere, and you have less precipitation, and that causes something called desertification, where if you clear cut a forest and don't immediately replant, a lot of this area becomes incredibly dry and turns to desert. You have soil loss and erosion as a result too, because now you don't have any roots holding the soil together. All right, invasive species are species that are non-native to an area, and they've usually been brought there due to human activity. So trade routes, they, for instance, latch themselves onto the bottoms of boats, which I'll give you an example of here in a second. They hitchhike along with us as we travel, and some of us actually deliberately move them for pets or decorations or ornaments. And the consequence is that they disrupt ecosystems and they decrease biodiversity. So stink bugs are a common example in the US. Kudzu is a plant. Two that I'm going to talk about here. The loosestrife, it's actually pretty, but it's not native to the Americas. It's native to Europe and Asia. It was actually brought over because it was pretty. It was an ornamental plant, but then kind of escaped and lives pretty much everywhere. It lives in wetlands, lives in ditches on roadsides, and basically crowds out native species. It outcompetes with them. It removes and destroys nesting and mating areas for a lot of birds and other organisms, and it's just an overall negative for the environment that it finds itself in. Another example, and actually the one that I was referring to earlier, zebra mussels were brought to the U.S. in their larval stage because they can attach to boats, for instance, and deposited in local bodies of water. And that's what happened in the Great Lakes. And they basically park themselves on any solid, non-moving surface, and they filter feed. And they filter feed and reduce other available food sources for fish and amphibians and other and crustaceans and other mollusks, and they actually attach themselves to water piping, and they can clog up water treatment facilities, and they don't have any natural predators. So this is another example of invasive species in the US. Overfishing, there's two more that we're going to do. Overfishing is the overexploitation of fish, but you can really overharvest really anything. This is made worse when there are no local or governmental regulations. This is called the tragedy of the commons, when you have a common communal resource that gets overused and is not regulated. But we're not going to talk really about that this year. AP Environmental Science actually covers that in more detail. So we have turned to things like aquaculture to try to get away from overfishing, which is basically growing fish farms and having fish nurseries. But there are consequences to aquaculture too, and you have to manage the waste and avoid pollution, etc. And you guys can look up more about the details of how that works if you want, but this is just the big overview. And freshwater resources. So we're not losing water on a planetary scale, but we are losing fresh water. We're converting too much of our fresh water to unusable forms of water. We're not cleaning the water properly. It's running off into oceans and becoming salt water, which at least for now is an irrecoverable form of water. It's too expensive to do it on a mass scale to convert it back to fresh. So we are losing freshwater resources. And if you've ever been out to the Grand Canyon, the Colorado River used to be a proud, mighty, strong flowing river, and it's basically a little stream. And there's actually a whole lot of political battles called the California Water Wars. Basically, you have all of these major cities out there that are tapping into that fresh water supply and competing with each other because the sheer number of people is not something that our current freshwater resources can sustain. So environmental issue number 9. Basically, humans mess everything up. The last one here is biological magnification. This is the increase in the concentration of a toxin or a substance that makes its way up the food chain. So as your consumers eat producers, and as your secondary consumers eat your primary consumers, etc., these toxins accumulate in fat tissue and is consumed ultimately by us, potentially. And by the time it gets to us, whatever it is, it might be in highly toxic concentrations. An example of these types of substances include PCBs. DDT is a insect repellent that actually ended up causing eggshells to thin, but it does not degrade. It actually, when birds would sit on their eggs, they would crack their own eggs and they'd kill their own chicks. Mercury, arsenic, so these are all toxins, and when they make their way into water supplies, they slowly accumulate in concentration because they're never processed, they're never broken down, they just kind of sit in the tissue and accumulate and accumulate. And as the consumers eat whatever's underneath them in their trophic levels, they accumulate all of that too. So the amounts, the units of these slowly increase as you go up the food web. And this is why if you ever eat a lot of tuna, or you might hear, if you eat a lot of tuna, you might have a lot of mercury in your hair, or you have high mercury levels. And before I leave you, I know this video is a little bit lengthy, but I think you'll find this to be interesting. When I was in college, I was in a biology lab, and I did not partake in the experiment, but basically everyone gave a hair sample, and from that hair sample, they measured the amount of mercury, and the amount of mercury in your body taken from your hair was directly related to the amount of tuna that you ate. And that's a real life, right now, right here example of biological magnification. So by all means, eat tuna. You're not going to die of mercury poisoning, but there is enough mercury to show up in your hair if you eat fish like that, and it is enough to distinguish you from people who do eat less of those fish, like tuna. So I hope this helped. I hope it helped you get a broader appreciation for our impact on the environment, perhaps give you a flavor of what environmental science courses might be like. And we'll talk more about this in class as you wish. So I'll see you then.